Okay, we use this example probably in the Zoom, but again, you never quite know with a 30-minute Zoom lesson and other things to talk about what you'll get to, so I'm just going to cover this right here. If I have the following cards, and I actually do have the following cards, they're right here. The question is, what is the probability of drawing a red card, placing it back in the cards, shuffling them up, and then drawing a red card again? And so if I were to mix these up, I'm going to hold them toward the camera so you can see which one I'm drawing, but then it occurs to me that I'm looking at my own face on the camera. So just so you know I'm not cheating, I'm going to wear a blindfold. Guess I don't need glasses when wearing a blindfold. So you can see the cards and I can't. I'm mixing them up. What's the probability that I would draw a red card at random, like that, put it back in the deck of cards, mix them up, and then randomly draw another red card, like that? We can calculate that probability. It's funny doing it with a blindfold on because I actually don't know if I did it. I guess I'll know when I edit the video. But, oh, there's another way you could do that. I could just keep doing it. I could keep doing it until I get it and just only edit out all attempts except for that attempt. But that's not what I did. I got it on the first try. The probability of pulling a red card, then pulling another red card is equal to the probability of getting a red card multiplied by the probability of getting a red card. The probability of getting a red card, since there are 6 cards and 2 of them are red, is 2/6. And because I replace the red card and mix them back up, the probability of getting the second red card is also 2/6. These are independent events because I placed it back in the deck of cards. So it's like the kind of problems we practiced last week. These are each a third, and a third multiplied by a third is 1/9. So the probability of pulling a red card, mixing them up, and randomly pulling another red card like I just did is 1/9 probability. We already answered that question. These are independent events because I placed the card back in the deck. If I take these same cards, what is the probability of drawing a red card, not replacing it back into the cards, and then drawing a red card again? So let's try this one. Blindfold. I'll show you I have the same cards. I'm not looking at the cards. I'm mixing them up. And what's the probability we'll draw a red card at random, like that, not replace it, mix the cards up again, and draw the other red card? What's the probability of doing that? I'm going to see if I have only black cards left. Oh, I do. Amazing. Okay, this is different than the last one. It's actually more difficult than the last one. The probability of getting the first red card is no different than what we did before because there were 2 red cards and 6 total cards. But because we are not replacing it, it doesn't matter which one you cross out, or you could just cover it with your thumb or something, but pretend that red card is no longer in the deck. The probability of red after the first red card has been drawn and not replaced would be, now there's only 1 red card, 1 favorable outcome, and fewer possible outcomes because there's 1 fewer card, so 1/5 probability. And this is still a third, but when you multiply those, it's even less likely than the previous sequence of events because it's 1/15 probability. These are dependent events because the likelihood of drawing that second red card was influenced by the first event. When you draw that first red card and don't replace it in the deck, you've reduced the number of favorable outcomes and also reduced the number of possible outcomes. And so this second probability is changed based on what happened with the first. If we had drawn a black card and not replaced it, it would be easier to draw the next card as a red card. And so that's, other than that, you simplify and multiply like we were doing last week, but this is just a little bit harder. You have to think about how the second event is influenced and how that probability has changed. Now, this next question is particularly important for your next learning opportunity, which I'm sure I explained in the Zoom, but it's more important that you get the practice on the notes today, because I'm making tomorrow's math class doing the learning opportunity. So you could actually not start the learning opportunity until tomorrow, and then do it tomorrow, grade it tomorrow, and get me the grade, and that's what will count as tomorrow's math class. So today let's focus on the notes and using the Nearpod to finish the notes, and then tomorrow you get the learning opportunity done. But there's something tricky about the learning opportunity. I'm going to try to put you in a better position with this problem. What would be the probability of getting 2 red cards if you just mixed up the cards and tried to pull 2 at the same time? How would you calculate that? And the weird thing about this, and I didn't actually know this until I started playing around with these kind of problems some years back before I started teaching this, if you're pulling 2 cards at once, that's considered dependent events. These are dependent. And the way I like to think about it, a situation like this, it's like you can't pull them both at exactly the same time. So imagine that you're pulling one a millisecond before the other. Even though you're pulling 2 out, the second one can't be the first one. So it is happening after the first one, even if it feels like they're happening simultaneously. So the first one, the probability of pulling the first one is 2/6, which of course is 1/3. But then when you multiply by the probability of the second one, you have to think of it as happening after the first one. And so we've already said that if one of them was gone, let's make it this one this time because it doesn't really matter, there'd be a 1/5 probability of getting the other red card. And so this is 1/15. Because a situation like this, you are dealing with dependent events, so you should calculate them that way.